Hello, I'm Maurice Dupre, and in this section we're going to discuss implicit differentiation. Remember, the basic problem of calculus and differential calculus is to develop methods for finding tangent lines to curves. We generally begin assuming the curve is given as a function, the graph of a function, but in general, curves are not graphs of functions. What do we do in general? Let's look at a picture. Here, for implicit differentiation, I've drawn a picture of an arbitrary curve in the plane. You can think of f of x comma y as standing for some expression involving x and y, and it's set equal to 0. And so here I have an equation in x and y. And of course, we think of the graph of such an equation, the set of all x, y, which satisfy the equation, as being some curve in the plane in general. Now, suppose I've located a point on that curve, that is, I found a pair a comma b specifically satisfying the equation, so f of a comma b equals 0. From that information, what I would like to do is also be able to find the equation of the tangent line to the curve through that point. For instance, if I were trying to graph this curve, and it's hard to find an expression for y in terms of x because the expression might be very complicated and I can't solve for y as a function of x. In that case, one strategy might be if I find a point on the curve which satisfies the equation, then if I can find the tangent line, I can imagine, notice the curve stays close to the tangent line if I don't move too far from that point, so I could move over a little bit off the tangent line and try the same strategy again, getting a new tangent line, and thereby kind of build an approximation to the curve near this point. Well, in any case, how can we get the equation of the tangent line? Somehow we have to get an expression that we can differentiate. Well, notice if I look at a little piece of this curve around that point, so look between my fingers here, the little piece of that curve, just this little piece, that is the graph of a function. And so we can imagine that in theory, y could be expressed as some function of x. If the y were replaced by that function of x, this would be an equation involving x alone, wouldn't it? If I differentiate that equation, then I have to get 0, but using the rules of differentiation, the derivative of that expression would appear in various places and we could solve for it. And that's the idea of implicit differentiation. This equation near this point a comma b implicitly is defining y as a function of x. We say y is implicitly defined as a function of x there, and this equation defining y implicitly as a function of x, when differentiated, will allow us to implicitly get an equation for the derivative. Of course, our expression will involve x and y. Well, let's look at the exact procedure for getting the implicit derivative of y with respect to x when x and y are related through an equation. Implicit differentiation. 1. Differentiate both sides of the equation with respect to x, treating y as a differentiable function of x. 2. Collect the terms with dy dx on one side of the equation. 3. Solve for dy dx. Let's apply the procedure for implicit differentiation to get the derivative of y with respect to x in the case where we have an equation relating x and y. Here I have the equation x squared y plus xy squared equals 6. And so remember, the first step, differentiate both sides of the equation with respect to x, treating y as a differentiable function of x. So even though I'm seeing y, I want to think of it as some expression involving x. In fact, for the moment here, I'm going to actually replace y by some expression f of x. That is, we know implicitly it's defined as a function of x by the equation wherever the differentiation process can actually work. And so I'll replace the y at first by f of x. And so there's our equation. Now we can differentiate that expression with respect to x on both sides easily. We don't know what f of x is, so consequently whenever I run into differentiating f of x, I would just use df dx or dy dx. So here, in effect, we're letting y equal f of x. Some function of x, we don't know what it is. So let's differentiate the left side. The first term, by the product rule, has derivative 2x times f of x plus x squared times the derivative of f of x. Well, we don't know what f of x is, so we can just write f prime of x for that derivative. Now we differentiate the second term. Derivative of x is 1 times f of x quantity squared plus x times the derivative of the second factor, which is, well, our chain rule tells us that will be 2 f of x times f prime of x. Now, let's do this again on the left side, but this time instead of replacing the y by f of x, I'm going to work directly on the original expression. It has fewer symbols. X squared y plus xy squared equals 6. Let's differentiate the left-hand side. Okay, so the derivative of the first term, well, it's the product rule, 2x times y plus x squared times the derivative of y. Well, look up here. Y is f of x, so the derivative of y is f prime of x. So we just write dy dx in this case. Plus, derivative of x is 1 times y squared plus x times the derivative of y squared. Remember, the y squared is the f of x squared, so when I differentiate it, that becomes, by the chain rule, 2f of x, f prime of x, or in this case, 2y dy dx. And of course, we equate that to the derivative of the right side. Of course, that's easy in this case. Derivative of 6 is 0. So you see, even though I could replace y by f of x everywhere here, thinking of f of x as some implicitly defined function through the equation without actually solving the equation for y in terms of x. But there are more symbols to deal with, so it's best to get used to dealing with just the x and the y. So whenever I differentiate an expression in y, it's done by simply differentiating with respect to the variable y and multiplying the result by dy dx. That's what the chain rule says. Remember, the chain rule says that to differentiate with respect to x some function, call it capital G of y, you would get g prime of y, the derivative with respect to y, multiplied by dy dx, or for emphasis, dg dy times dy dx. Well, we don't know what y is in terms of x, and so wherever we run into having to write dy dx, we just leave it as dy dx. But if I have the expression for g in terms of y, I can actually compute dg dy, which will be an expression in y. So just like here, to differentiate y squared, we get 2y dy dx. Now notice that every term in this equation either does not involve dy dx, or when it does involve dy dx, it's merely to the first power. That's because the chain rule here is saying the result of differentiating some function of y is going to be some expression involving y multiplied by the symbols dy over dx. And so consequently, there can never be any other powers of dy dx other than the 0 power or the 1 power. And consequently, it's extremely easy to solve this equation for dy dx in terms of x and y. Notice all I have to do is take all the terms which don't involve the dy dx, move them to the other side of the equation. Then I'll have left on the left side of the equation terms that do involve dy dx, and every one of them has a dy dx to the first power. So I simply factor out the dy dx, and then I have some expression in x and y multiplying by dy dx is equal to some other expression in x and y. And so let's do it now from the start, go through the whole process. Okay, so we start off with x squared y plus xy squared equals 6. And now we begin by differentiating both sides with respect to x. First term, 2xy plus x squared dy dx plus derivative of the second term, derivative of x is 1 times y squared plus x times 2y dy dx. The derivative of y squared with respect to x is, by the chain rule, 2y dy dx. That's all equal to 0. Take the two terms here without the dy dx, move them to the right-hand side. So we're left with x squared dy dx plus 2xy dy dx equals negative 2xy minus y squared. Factor out the dy dx. So we have x squared plus 2xy all times dy dx equals, and I'm just going to write this, negative 2xy plus y squared. And so now just divide both sides by the x squared plus 2xy, resulting in dy dx is the negative of the quantity 2xy plus y squared, all divided by x squared plus 2xy. So see, we've ended up with an expression for dy dx which involves only x and y. Of course, if I knew y as a function of x, I could put that in for y, and the derivative would then be expressed entirely in terms of x. Another thing to keep in mind is if I actually had the coordinates of a single point on this curve, that would mean I would know the x-coordinate and y-coordinate of the point satisfying the equation. I could put those coordinates in, and then I would get an actual number telling me the slope of the tangent line at that specific point. So the implicit derivative can be used to get tangent lines to curves given by equations at points where we know the coordinates of the points. Let's use our process of implicit differentiation to calculate an implicit derivative starting with an equation in x and y. Here I have the equation 2xy plus y squared equals x plus y. And we want to find the implicit derivative of y with respect to x. So remember, step 1, differentiate both sides of the equation treating y as some function of x. So for instance, when I differentiate the y squared as a function of x has to be differentiated with the chain rule. It's the derivative of y squared with respect to y, which is 2y, multiplied by dy dx. So let's begin. Derivative of 2xy, we use the product rule on the first term. We get 2 times 1 is 2 times y, plus, now copy the first factor 2x and multiply by the derivative of y with respect to x. That's dy dx, since we don't know exactly what y is in terms of x. Now for the second term, the derivative of y squared with respect to x, well, the chain rule says differentiate it with respect to y, that would be 2y, times the derivative of y with respect to x, whatever that is, equals the derivative of x is 1 plus the derivative of y is dy dx. You might notice this is a specific case of something that's very typical in mathematics, and that is if you don't know what something is, but you have a symbol for it that'll fit into your proceedings, just go ahead and proceed and put that symbol in everywhere. Maybe you'll be able to get an equation which you can solve for the unknown item. And that's what we're doing here. Notice we have an equation. Every term either involves dy dx raised to the power 1 or doesn't have dy dx at all. And so we move all the terms with dy dx to the left. So I'll have 2x dy dx plus 2y dy dx minus dy dx equals 1. And what do we have over on the left side without dy dx? Simply the 2y. It comes over to this side, minus 2y. So we have 1 minus 2y on the right. Now to solve this for dy dx is very easy. All I have to do is factor the dy dx out. So I have 2x plus 2y minus 1, all multiplying by dy dx equals 1 minus 2y. And so finally, now I easily solve for dy dx. dy dx is equal to 1 minus 2y, all divided by the quantity 2x plus 2y minus 1. Let's look at another example where we use implicit differentiation to find an expression for the derivative of y with respect to x. Here I have the equation y squared equals the quantity x minus 1 divided by the quantity x plus 1. Notice that we could solve for y as a function of x easily here. We would have y equals plus or minus the square root of the quantity x minus 1 over x plus 1. That is, if you give me a specific point satisfying this equation, then it's either going to satisfy the equation here with a plus sign or with the minus sign. And so consequently, I've got two ways to define y as a function of x, and any point on this curve is on the graph of one of these two functions. But let's go directly to implicit differentiation and calculate the implicit derivative. The derivative of y squared with respect to x is simply 2y times dy dx. That's equal to the derivative of the right-hand side with respect to x. There we just used the quotient rule. The derivative of the numerator is 1 times the denominator minus, and now copy the numerator and multiply by the derivative of the denominator, which is clearly just 1. And then remember to divide by the square of the denominator. Well, notice x minus x, the x's cancel. 1 minus a minus 1, that's 2. So this amounts to 2 divided by x plus 1 quantity squared. Well, notice what's going to happen here. The 2's cancel, and so I'll simply get dy dx equals 1 over the quantity y times the quantity x plus 1 squared. One thing you can notice here is I could replace this y by one of these functions, that is, one of these expressions for y in terms of x, if I knew which one I was really dealing with. And when I did that, I would have dy dx as a function of x alone. But in any case, this expression will be valid no matter which one of those functions we're dealing with. We've seen that we can easily differentiate both sides of an equation with respect to x whenever we have an equation in x and y, and thereby determine the implicit derivative of y with respect to x. This method can be extended to give higher derivatives of y with respect to x implicitly. Let's see how this is done. Higher implicit derivatives. Differentiating the equation f of xy equals 0 results in an equation of the form some function g of xy multiplied by dy dx equals some function h of xy. That is, our equation after differentiation always has the form some expression in x and y multiplied by dy dx equals some other expression in x and y. So typically we would now divide both sides by g of x comma y, that is, divide both sides by whatever expression multiplies dy dx, and that would solve for dy dx, giving the implicit derivative. But on the other hand, suppose we want the second derivative of y with respect to x. All I have to do is take this equation and differentiate again. When I differentiate the second time, notice in here, I will get terms involving dy dx, and over here I'll have terms involving dy dx. But of course, from this equation, I already know what dy dx is easily. It's h of xy over g of xy. And so consequently, the one term that I'll be looking for is the term that has d squared y over dx squared. In effect, by differentiating both sides of that equation, I get an equation that's easily solved for the second derivative d squared y dx squared, or y double prime. And that method can be extended indefinitely. We can just keep differentiating the equation and get ever higher derivatives of y with respect to x expressed implicitly in terms of x, y, and all the lower derivatives, which once we've already got the lower derivatives expressed in terms of x and y, we put those expressions in, and everything's in terms of x and y alone. Let's use our method of implicit differentiation and as extended to find higher order derivatives to find first and second implicit derivatives of y with respect to x. Find dy dx and d squared y dx squared for the equation x squared plus y squared equals 1. That is, this equation x squared plus y squared equals 1 defines y implicitly as a function of x. Well, obviously we know that's the equation of the unit circle, and so y is either the square root of 1 minus x squared or it's the negative of the square root of 1 minus x squared. But in any case, let's see how implicit differentiation works here, and in fact it makes it easier to differentiate. So to begin, we differentiate both sides of the equation. The derivative of x squared is 2x, and the derivative of y squared with respect to x by our chain rule is 2y dy dx. That has to equal the derivative of the right side, which is 0. Notice we can cancel 2's here, and so we have canceling 2's simply x plus y dy dx equals 0, and that would give us, for our implicit derivative of y with respect to x, simply dy dx equals the negative of x divided by y. Now, our next step to find d squared y dx squared is to go back to this equation and simply differentiate everything with respect to x again. The first term has derivative 1. We've canceled the 2, so we get 1 plus, now for the second term, which is the product y dy dx, the derivative of y is dy dx, so the product rule tells us we have two terms. The first one, the derivative of y times the second term, which is also dy dx, plus y times the derivative of the second term, which is d squared y dx squared, and that equals 0. Notice our second derivative has popped out here. It's to the first power. Every term either has the second derivative to the first power or doesn't have it at all. And so here we have the equation 1 plus dy dx quantity squared plus y times d squared y dx squared equals 0. Of course, that's a very easy equation to solve for d squared y dx squared. If I solve it right now, what I'll have is d squared y dx squared expressed in terms of 1. There doesn't happen to be an x, but there could be x and y and dy dx squared. Well, We know what dy dx is. It's negative x over y at this point, and so the square of dy dx is x squared over y squared. So now at this point I have the equation 1 plus x squared over y squared plus y d squared y dx squared equals 0. You see, no matter how bad this expression got in terms of dy dx, since I've already found dy dx, I'm just going to replace it everywhere by its expression in terms of x and y. And the result is some possibly bigger and more complicated equation, but it's still easy to solve for d squared y dx squared. Just move the terms without the d squared y dx squared to the other side and then solve. So you see, in this case, we obviously have d squared y dx squared equals the negative of the quantity 1 plus x squared over y squared, all divided by y. Let's use our methods of implicit differentiation to actually find tangent line and normal line to a curve given by an equation at a specific point. Find equations of the tangent and normal lines at the point 2, 3 to the curve with equation x squared plus xy minus y squared equals 1. Notice if I take x and replace it by 2 everywhere and take the y and replace it by 3 everywhere in this equation, I get 4 plus 6 is 10. Minus 3 squared, well, 10 minus 9, that's 1. And so the point 2, 3 satisfies the equation. It's a point on the curve defined by that equation. And so we want to find the equation of the tangent and normal lines at that point. So in order to do that, we need the slope of the tangent line. To do that, we get the implicit derivative of y with respect to x. So differentiate both sides with respect to x, treating y as a function of x. Now this time, instead of using the notation dy dx, I'm just going to use y prime. So that means I'm going to use y prime equals dy dx. Just to save on space, it will often make the computations run a little bit more smoothly. So let's begin. The derivative of x squared is 2x plus. Now I have to differentiate the product of x and y. The derivative of x is 1 times y plus x times the derivative of y. I'll just write y prime. Minus the derivative of y squared with respect to x is, according to the chain rule, 2y dy dx, which I'll just write as y prime, equals, and now on the right side the derivative of 1 is 0. So again, as usual, notice every term either involves dy dx, that is, it either involves y prime to simply the first power, or it's not there at all. So move the terms without the y prime to the other side. We get, factoring out the y prime, x minus 2y, y prime equals negative 2x minus y. So let's solve for y prime. That will give us y prime equals, and now I can reverse the order of those two terms and change those to plus. We get 2x plus y divided by 2y minus x. There's our implicit derivative for y with respect to x expressed in terms of x and y. That's valid at any point where y actually is a function of x. And so notice at this particular point 2, 3, I can replace everywhere the x by 2 and the y by 3. Well, what happens? 2 times 2 is 4, plus 3 is 7. The numerator becomes 7. 2 times 3 is 6, minus 2 is 4, so 7/4. So y prime at 2, 3 equals 7/4. That's the tangent slope. So we can easily write the equation of the tangent line in point-slope form. It's simply y equals 7/4 times the quantity x minus 2 plus 3. How about the normal line? Well, remember, the normal line is simply perpendicular to the tangent line, and so all I do is replace the 7/4 by the negative reciprocal, negative 4/7. So we would have the equation y equals negative 4/7 x minus 2 plus 3. So here's the tangent line, and here's the normal. So there's the answer to our question. Notice it falls right out from implicit differentiation. Well, we've seen that when y is related to x through a general equation, we can get the implicit derivative of y with respect to x expressed as a function or expression involving both x and y. Then if we have an explicit point on the curve of the equation, that is, we have the actual coordinates of that point, we can put it into the implicit derivative to get the equation of the tangent line.